So I'm going to outline something slightly different from this morning, but also put it in the same context as what we saw. Like it or not, we've protected our data at rest and over the air. The gap that we have as cryptographers is in process. It is possible within a process that's running to be able to determine the keys, the encrypted content, and so on. Fully homomorphic encryption is the holy grail for cryptographers. We're not there yet, but perhaps over the next few years, especially with the rise of ASICs and hardware and GPUs, we will see the opportunity to encrypt data in every single state. In fact, from the sensor right to the consumer, we will have encrypted data. Not TLS tunnels. They're terrible. A TLS tunnel has a proxy in between often. Between my website and me is Cloudflare, who breaks the tunnel. The user doesn't know about that and inspects all the traffic. TLS is a machine-to-machine and not a sensor-to-sensor. So I'm going to outline some of the move towards fully homomorphic encryption. Some of you may know me. I've created this website. Why? Because I'm really in love with the subject. I love everything about cryptography, and I want to document as much as I can. It's a free website. There are no advertisements on it at all. Even though many companies ask for advertisements, I have no advertisements in there. It is used by 1.2 million unique users every single year and has about 30 million accesses. So cryptography is big business overall. Okay, that's the website there, if you want to go to it. A little bit generic, I know. And when it comes to OpenSSL, then I've got examples there. If you're interested, that's how to use the command line, the CLI, and then that's how to use C++ with OpenSSL. And then whenever something new comes out, it's amazing. 3.5 was such a quantum leap. We went from 1 to 3. You did know that we missed 2 in between. Don't know why that was, but we kind of jumped from 1. We stuck at 1 for a long time. I remember 0.89 from the original, and then we went to 1. Then we had Heartbleed, which was an exciting time, fun, exciting time. But then 3.5 has came along, and it gives us the opportunity to migrate towards post-quantum cryptography. So why am I here? Well, I got into cryptography reading this book here by Bruce Schneier, and it completely inspired me. And really, it was him talking about public key cryptography that I could just see the opportunities that were there. We could actually start to properly encrypt, digitally sign things, and so on. And it was actually the paper outlined A and B, Bob and Alice, but it was Bruce Schneier who filled in all the other ones, Carol, Dave, Faith. The two I like are these two here, Victor and Peggy. Peggy is the prover, and Victor is the verifier. Great. And the PKI is all about this person here, Trent. So it was Bruce that thought up all these names, fill in whatever name. But unfortunately, we have our adversaries, Eve and Mallory, in there. So it's all change. And this is what we talked about this morning. This is where we're moving. And people have said to me, stop talking about quantum. It's not about quantum. Let's just say this is a migration. We went from RC4 to, to AES and so on. We've migrated cryptography very well over the years. So this is us just having a little refresh and moving away from the methods that we've used in the past. And it's not just public key, it's also symmetric key and hashing. So don't forget that Grover's algorithm breaks, or could break, our existing symmetric key and hashing methods. So this is the migration that we're going to have, and many of these methods that we have, like it or not, lattice was the one that won. Lattice, relatively small keys, relatively small ciphertext, and good performance compared to the hashing methods. So that's the migration. And really, I've been lucky to speak to some of these people, but these people built, who's that? Ah, the boy genius. You know these ones, yeah? This one, they're looking young here. This one, Diffin Hellman. This one is easy, Revest, Shamir, and Edelman. This one, you're using it right now if you're in blockchain. Ralph Merkle. Ralph Merkle created the Merkle tree that is now the backbone of our hash-based post-quantum cryptography methods. So all these people 50 years ago, perhaps 20 years ago, these two people, you know this one? He's looking rather young there. That's now Kobolitz, and that's Victor S. Miller. I've been so lucky to speak to those. Elliptic curve, they created it. No one was interested. It took years for the paper to be even cited a reasonable amount of times. But it's changed our world. It's changed our world. The elliptic curve is the default now for key exchange. And for signatures, it's just so much better than RSA. Then we see Craig Gentry come along with a new method of creating fully homomorphic encryption. And I hope Daniel's in the audience somewhere. But Daniel DJB has created many of the standards that we're now, or several of the standards that we're now looking at for post-quantum cryptography. But all that's going to go. It's all changing. So for years, we've used partial homomorphic encryption. And if you've got an addition function or a subtraction, then you can use something like Paleo or Elgamal. But it doesn't give you the full gambit of all the methods that you want to use. I want to multiply, divide, subtract, and the other one. But these methods don't give you that, where fully homomorphic encryption gives you all of the methods. So it was Tahir Elgamal who created his public key method that has homomorphic properties that allows us to multiply values together homomorphically. And then it was Pascal Paleo here. This is Pascal here. Look at the citations on this. It's a real slow burner. And oh boy, is it taking off there. So Pascal came up with a method where we can add and subtract. And think about it. Many of the applications that we have are just basically adding up things. So this is an excellent method for us to be able to just use addition and subtraction. The problem, though, is these little things here, discrete logarithms. And Shor's algorithm showed that discrete logarithms and elliptic curve methods that are kind of derived from them can be broken. So fully homomorphic encryption looks at the opportunity of having a key pair and then encrypting the data with the public key here, and then processing the data, and the only key that will decrypt will be the private key. And isn't that a wonderful scenario? Is that if Bob encrypts his data with that public key, no other private key apart from that one can actually decrypt that data or process that data, which means that Bob can lock the data in automatically to say that this data shall only be used for this processing purpose. We can also use symmetric key, so we can use the same key to encrypt and decrypt, but why would you do that? So this method, typically not used. We would use asymmetric encryption to be able to do our processing. So, sorry to show you some maths, but this is the formalization of it. This is an operator, and we can encrypt the data and then still do the same operation. And the actual maths, and it's strange for me as a teacher, because I've taught elliptic curve and RSA and discrete logs for years. And now I've got to rip that up and start to teach a little bit about polynomials. So it basically works like this. These are our polynomial values. And these are equivalent to little vectors that occur in space. If you think that's a multi-dimensional vector, I could represent that as a vector 32, 26, 135, 44, 63. That's a vector in space. And all we end up with is a whole lot of vector and matrix multiplications. That's at the core of neural networks, and that's at the core of fully homomorphic encryption. And then, I don't know if you've ever played around with things. When you do your public key methods, you've got to inverse the method. You take the inverse of a value, mod p. And it's the same in this homomorphic world, in that you can take your polynomial and you can find the inverse. So if I multiply with one polynomial, I find the inverse of it, I multiply it again, and I'll get my plain text back again. And this is the basis of our lattice methods. It's all based on learning with errors, or typically what we could define as ring learning with errors. We have a secret, we have a well-known public value, and then we add errors into it. And like it or not, it's really difficult to find out from this value what the value of the secret value is because of these errors. But these matrices are 1,000 or 2,000 values large, so they're very large matrices. And that's the new hard problem that hopefully our quantum computers will not be able to break. So it's went through 3 or 4 main generations. First was a simple method from Craig Gentry, but then that was advanced on to BGV and BFV, which allow us to be able to operate fully homomorphically on integer values. So if your application purely involves integers, then that's a good application. It was a big step forward when it came to using floating point values, and that's ZKKS. And then there was one in between that allows us to be able to not just create with floating point numbers or integers, but with circuits, and that's with the DM method that we have here. So this is basically what we have. We have our public key, which will encrypt the data. It can go into a data processor in the cloud, and the EU is building a homomorphic cloud in a few projects. So perhaps the EU will be building this data processing engine for fully homomorphic encryption. And then the private key is then used to be able to decrypt. The problem here is obviously the data processor could have access to the private key even though it's in a secure enclave. So an even better model is that you ship the ciphertext off, and Wendy, the consumer, has the private key in her secure enclave. So all the data in here is encrypted. All that needs to happen is that the consumer needs to pass to the processor what the public key actually is. Where this gets really interesting is that we can start to look at machine learning processing. And this is a big problem just now. Our data is being harvested like anything. So these large language models are harvesting citizen data continually, and they're using it on plain text. So fully homomorphic encryption with machine learning will allow us to be able to process on encrypted data. And especially for crowdsourced data, this could be really useful. And then we can actually have federated models where we can have multiple entities training models homomorphically. And it's likely that the cloud will not be centralized anymore. We will push our processing right to the gateways. Cloudflare, for example, has invested massively in GPUs that are right at the edge of the cloud and as near to the consumer as possible. So our models of the future are likely to involve GPUs that are actually right at the edge. And these could process homomorphic data for us. So what I'd like to do is to outline, this is some of the maths, if you're interested. This is the sizes that we have for our polynomials. We can see they can get quite large, 32K in this case. So the memory consumption tends to be fairly large overall. So this is BFE, and then CKKS allows us to operate on our floating point values. Where this gets really interesting is that we can now build electronic circuits. So it is now possible for us to actually build any circuit that is required, any logic, as a Boolean circuit overall, and then implement it homomorphically. This is a method called DM or FHEW, and these were the papers that actually created these methods there. So I'd like to outline one library, and there are many libraries around. OpenSSL doesn't support it at the current time, but there was a library called Palisade, and then that's now been created as OpenFHE. And I think it's one of the best libraries around. You can use C or Python to implement fully homomorphic encryption. Okay, a couple of little principles first. When we're multiplying these vectors with noises, the noise will multiply. If I take a little error and another little error, multiply the two values together, I'll get a larger error. Eventually, that error will keep growing large, and it will swamp the actual signal. So it was Craig Gentry that actually came up with a method where we could get an encrypted version of the private key to be able to clean up the processing after all these multiplications. The unfortunate thing is that this is the thing that slows it down. Because we're doing all these multiplications, we need to do a bootstrap every now and then. So this is one of the reasons that homomorphic encryption is still relatively slow and processor intensive. We can also have what's called slots within our homomorphic encryption. If we have the same task to complete many times, we can fill in a number of slots, and it will do the processing almost in parallel. Okay, so I'll give you some examples. This is sorry to scare you a little here, but this is the C code over here, just to show how this is actually implemented. There is what's called a multiplication depth, and this will be the number of times we can multiply before we have to bootstrap. So the larger that value will be, the more the noise is likely to build up. This is the key pair generation here that we have, and we have some features that we can set, and this defines the plaintext modulus. So the whole thing with prime numbers doesn't go away. We're still dealing with mod p. It's just this time we're dealing with a polynomial mod p. Okay, so there's an example in there for CKKS. So there are many methods that we can actually use. In this case, I've used an evaluate add. In this one here, we take our plain text, and we need to convert it into polynomial. So this is an integer, and it will convert it into polynomial here. Once we've got our plain text polynomials, we can then operate them by encrypting with a public key to get our ciphertext, and then we just basically, in this case, we add the two numbers together. Quite simple, but extremely powerful when you think about it. There is no, apart from the x value and the y value, there's no values actually revealed there. There's the multiplying two values together. We can see here. This is some of the functions that we have overall. The batch processing that I showed you, it's possible to create the same function multiple times, and then it will speed up the main operation. As I said, where this gets really interesting is that we can break down any logic into and add gates. So any logic that you would need can now be defined as a Boolean circuit, and then that can be implemented with inside our code. So homomorphic encryption isn't just for integers and floating point values, it can be for logic values too. It's a more complex example. This is just a circuit to add two numbers together, but we can actually build a completely homomorphically encrypted library with all of the logic that we would have with inside our program. Okay, there's a simple one for a multiplex circuit. C is the switching element here, and this one is a majority circuit in there. And we can see that we can just create our functions fairly easily. If you've ever done Shamir shares, you'll know that it's possible to split a key into shares and then do a multi-party computation on it, such as creating a signature which is robust. In fully homomorphic encryption, we can split the key and then we can get each of the entities to actually process for that value. In this way, we implement MPC or multi-party computation. One interesting area, and it was Chebyshev who said that mathematical functions can be represented as a polynomial. So we can take a sine x, cos x, tan x, or a square, and we can implement it as a polynomial value. And this makes it highly efficient in that we can convert everything that we're doing into a polynomial. There's a method called proxy re-encryption, if you've ever implemented it. And it's basically taking something that's been encrypted with Alice's public key and converting it in some way so that it is now encrypted with Bob's public key. And fully homomorphic encryption allows us to implement this type of method. We can implement polynomials with it. But where this should become a standard is that we should stop using plain text to train machine learning models. So what we need is we need something that looks like a neural network. And this is called an activation function that we would get, and we can implement this within homomorphic encryption. Then we can operate on matrices. So a lot of the calculations that we do within a neural network involve matrix and vector multiplications. And basically, a neural network is made up of nodes with weightings, and this can easily be represented as a vector input and a matrix multiplication here. So if we can implement this type of operation homomorphically, we can start to create a neural network which is fully encrypted. Okay, so there's an example there. We just encrypt our input data. There we have our weightings, and when we can decrypt our answer at the end of the neural network. Remember, LLMs are just neural networks. And below an LLM is a neural network that's been trained on data. If you're interested, there's the code that allows us to be able to do that vector and matrix multiplication overall. Okay, so then to build up a more complex neural network, basically we have a vector here, a matrix multiplication, and another matrix multiplication, and then we have a vector on the output. And this becomes our neural network overall. And then in the end, we have our input here, and hidden layers, just like our brain. These are activation functions that we saw, and they fire or not, depending upon the inputs and the weightings. And then we have our output vector there. That's an LLM under the hood. So what we do with an LLM is that we have a picture of a cat, and then we use a convolutional method to be able to extract features that then go into the neural network. The bitmap doesn't go straight into the neural network. We need it to create features. LLMs are now on trillions of features. ChatGPT 4 5 had over 1 trillion features that were fed into it. And then the output becomes a cat. So the opportunity is that we can use backpropagation to be able to train our fully homomorphic model. With this, we can look at the homomorphic encrypted outputs and then backpropagate to find the weightings that we actually need. In this way, we protect the citizens' privacy for the data that we're actually training the network on. So there's another method, support vector machine, that's used in many applications. And this was implemented by Stanford a few years ago in a genome study. And they took fully homomorphically encrypted data and trained the machine learning model on it. And what they found was that they got the exact same results, no matter if you used homomorphic encryption or not. So this actually proved that it was possible to use homomorphic encrypted data to be able to train models. The way it basically works with SVM is that you train it on plain text. So there are many test vectors and test sets that you can use. And this will allow us to be able to determine the weightings and the intercept values that feed into the SVM model. We then plug it straight in with OpenFHE with encrypted data as the input, and then we decrypt the output. Think about this. Credit card checking from banks. The data could be sent in from a bank, encrypted into an SVM cloud model that did the processing, and then sent back to the bank, encrypted. And then they can decrypt with the private key. So the applications of this are absolutely massive. But we need to make sure that banks and organizations with our data treat our data with respect. And luckily, as I said, the EU is working on homomorphic encrypted cloud processing infrastructures. So we ran a model. This is for SVM. So we varied the main parameters that were involved so we could actually see how these parameters varied the performance of fully homomorphic encryption. So this is with a non-GPU and just on a standard ARM processor. The accuracy was virtually perfect, so it didn't matter that much that we were using our homomorphically encrypted data. It was almost the same as the unhomomorphic encrypted data. Obviously, there's noise in there, but the accuracy is good. And then we varied each of the parameters that were involved and then looked at the speed up of the actual process. So the main data that we found is shown here. So when we increased the ring size, in this case, by a power of 2 in there, we doubled the processing time. So you can see here, as we get bigger ring sizes, then obviously it's going to take longer. So there's almost like a linear relationship here, but it gets more accurate. So our data becomes more accurate as we increase the ring dimensions. When we looked at the multiplication depth, or this MD, there wasn't that much variation, but it did matter if we actually set that value there. Okay, so I've got examples on the website there if you want to see them. I don't have a GPU underneath, so they might run a little bit slow, but hopefully you should see the possibilities. I know that OpenFHE is working with Intel just now and working on hardware. If we can get the GPUs and the ASIC devices to be homomorphically processing, then think of the opportunity of us actually taking encrypted data and then using that as our processing. Thank you.
You mentioned backpropagation. So are you going to train on the encrypted data your neural networks? Are you proposing to train neural networks on the encrypted data?
Yeah.
Isn't there a problem that basically by training neural networks, weights, basically revealing the data that this neural network being trained on, because you can use GAN and adversarial networks that basically reversing the neural networks and by exploring the latent space and thus revealing the data what the neural network is being trained on. Isn't that a concern?
I think if you had a lot of data, it's very difficult to reverse the data back that we actually have. So you wouldn't be training it on maybe one or two data elements that could be reversed back again. This would be large data sets that were homomorphically encrypted. The model weightings in the pure form will still be known, so they won't be protected. But I think it's possible in the future to actually have encrypted weightings within the neural network so that someone can't actually reverse the model from it.
Okay, thanks.
Hi. In your presentation, I hear that OpenFHE supports logistic function that you use the example of Chebyshev function. I think that function cannot be calculated accurately by FHE, and how to simulate it? How are they implemented? Does it implemented based on CKKS or TFHE, which is the base bit level homomorphic encryption?
So the problem, as you've identified, not all mathematical functions can relate to a Chebyshev function. Square root, some of those functions, but for the periodic ones, then it struggles. So you would have to fall back into a more traditional mode, as you said, perhaps with the bitwise operation where you would have to build the mathematical function back up again. It's certainly a weakness of the current models that we have.
So these functions in OpenFHE are currently implemented in TFHE?
Yeah.
Okay.
So maybe this is just my mathematical intuition only, but I understand that the expressiveness of neural networks is caused by nonlinearity. And if you will remove the nonlinearity to allow approximation, to allow this homomorphic-like transformation, you will need a much higher size of the neural network for the same expressiveness, even for single pair of public and private key pair, and even higher size, exponentially higher, to allow general pairs of key pairs to be used. So isn't there this problem?
Yeah, for a neural network, that's the problem. Obviously, when we're just taking our homomorphic encrypted data, we need to make sure the noise will never swamp the actual values that we have. But you're right, for a scale-up of a neural network, then it will have much more computation. But I think when we're building large arrays of GPUs just now, I think Microsoft and OpenAI are building one of the biggest data centers ever, and it's just filled with GPUs. I think that processing power may be there in the future, but it shouldn't stop us from actually having the ambition that we could actually train machine learning models with our encrypted data.
Thank you.
Hi, Jan here. Thanks a lot for a nice talk and also for the podcast. I'm not following FHE closely. I wonder about authenticity. I look up quickly some papers, so it seems that we don't have fully homomorphic encryption with authenticity. Do you have any comments on where's the research at?
Sorry, what was this? Could you say that? Repeat the question again.
So fully homomorphic encryption with authenticity.
With authenticity.
Authenticity.
Oh, yeah, that is a fundamental problem that we've got to watch, that the data isn't poisoned at the input. So we really need to trust the input values that we're having. There may be some checking at the gate when the data is initially encrypted. Then we look at the bounds of the data to make sure that it's correct data. Was that the problem that you're highlighting? Yeah, because obviously it would be easy for someone to poison the homomorphic encrypted data within our model. So we always need to make sure that the data is trustworthy, and there's some checking for bad values at the gate. But when you think of the opportunity that all of us could share our heart rate data here, and then we could actually look at training medical illness models for diabetes and so on. Apple are using homomorphic encrypted data fairly intensively with matching images. If you're beside the Eiffel Tower, Apple doesn't know that you're there, but can actually use homomorphic encryption with GPS coordinates to find images that are around the Eiffel Tower. Google used differential privacy, which I think is terrible, where you can add a little bit of noise, and across the population, the noise evens out. But for things like medical purposes, to add noise onto your heart rate really isn't a good thing. So I mean, I think the Apple Secure Cloud is looking like a good model for the future. I appreciate it's proprietary, but Apple are doing a lot of good work in terms of the privacy-aware methods and many companies have this problem that they want to collect statistics across a population. So what's the gender balance of the iPhone between male and female? With homomorphic encrypted data, it's possible for you to do that computation to end up to know that you have 60% male, 40% female without actually revealing that. At the present time, in many methods, that's done by differential privacy, but homomorphic encrypted data should improve on that.
Yeah, thanks for the talk. So we have time for one more quick question, I think, and then we're on to a break.
Yeah. Thanks for the talk. What do you think about verifiable computation in general with the usage of zero-knowledge proofs in this ecosystem of fully homomorphic machine learning?
That was the topic I didn't have the opportunity to present on, was zero-knowledge proofs. I think one problem is that if we are moving towards a latticed world, then a lot of our existing cryptographic primitives will struggle to scale. They tend to be based on pairing-based cryptography and elliptic curve cryptography. So there are many areas in lattice cryptography where there is a big gap that we need to actually fill. So I think a lot of the good cryptography that we do just now with elliptic curves, zero-knowledge proofs, and so on, we are struggling to find the equivalent. Shamir shares works in a lattice method. The Chebyshev kind of works there too. The proxy re-encryption works, but there is still gaps that we need to fill.